My name is Sanu Kumar. Currently, I am pursuing PhD in Electrical Communication Engineering Department, Indian Institute of Science, Bangalore. Today, I am here to describe my research work briefly on the topic a decision theoretic approach to angle of arrival estimation in MM-wave system via active learning. Now, these are the outline of my presentation, motivation and goal, followed by ongoing work, result and few references. Now, coming to the motivation, as we know, in wireless system, wireless channel characteristics vary over time. So key channel parameters such as angle of arrival must be tracked accurately. Because of hardware and resource constraints, it limits how much information can be obtained per measurement. So in order to obtain the complete information about the unknown angle of arrival at base station, sequential learning framework must be used. Now, coming to the goal of this research, the goal of the research is to design adaptive beamforming strategy using decision theoretic approach via active learning framework and evaluate the performance of the approach using various key performance metrics like probability of detection error, minimum mean square error, and posterior concentration under single RF and two RF uplink system. Now, in system model, here we assume by pilot a symbol is transmitted by UE to the base station, which is equipped by two RF chain. So at the base station, it receives the pilot symbol at two different RF chain using two combining vector, that is beamforming vector here, which is obtained via the previous belief about the true angle of arrival using either hierarchical posterior matching algorithm or Bayesian Kramer-Rao lower bound algorithm to get the that sum beam. And for once we received the two measurement at one sensing stage, it further processed to update the our belief about the true angle of arrival. Now coming to the approach, as I said here, we maintain a belief about the true angle of arrival, and based upon that we design some beam either using the hierarchical posterior matching or the BCRB, and once we get the sum beam, we will solve an optimization problem to get a difference beam. Once we have sum and difference beam both, we apply it as a combining vector at two RF chain at the base station and get the two measurement at each sensing stage, which is further processed to refine our belief about the true angle of arrival. These are the complete approach. Now coming to the result, here in result I showed the posterior versus angle of arrival curve. Here we see as the time sensing interval increases, the posterior distribution of the angle of arrival converges to true angle of arrival. Here we assumed the true angle of arrival is at -2 degree. So here we can clearly see that the two RF chain with some difference beam quickly attains a peak in the posterior distribution at correct angle of arrival.